Hello again. So in this session, I want to delve further into the details of this heat equation. So let's first take a look at this heat flux and kinematic heat flux that we talked about in the previous session, which is this W prime theta prime, and see what actually does it mean physically, okay? And how does this work actually, okay? So in general, we can get this W prime theta prime if you multiply the original signal of W and theta, which is the vertical velocity times the potential temperature. We can actually, and then take the average of that. We can what we can do is we can do the Reynolds decomposition here, and then get W bar plus W prime times theta bar plus theta prime, and then take the average of the whole thing. And this equals to, if we look at each term separately, W bar theta bar plus W prime theta bar plus W prime theta bar plus W bar theta prime bar, right? And we know from the Reynolds decomposition, these two terms are going to be 0. So we are only left with these two terms here, and which equal to W bar theta bar plus W prime theta prime bar. So this is where this W prime theta prime comes from, okay? So let's see how this flux works by moving thermal energy in the, say, atmosphere. Okay, it could be for any application, but here let's say for atmosphere. So first I want to investigate a nighttime case. So first we want to see a nighttime case. Say during nighttime with surface cooling. So we have surface cooling during nighttime. And what does this mean? This means that the surface is actually colder than the air above that, right? In terms of potential temperature. In terms of the potential temperature. So if we look at our cases, say we have theta here and we have z here, the profile of theta would look like something like this near the surface. So say here we have one air parcel here, and then this air parcel moves upward somewhere here, okay? So because it moves upward, so the W prime, this is the vertical velocity, is going to be positive for this particle, right? Air parcel or air particle. And then here it goes to another height, say ZE, and here we have ZP at first point. And then the temperature of that, here the temperature is higher. So the initial temperature was theta P, and then the final temperature is theta E. So what happens to the temperature? So theta prime in this movement, upward movement, is going to be theta p minus theta e, right? So the actual, let's say it has its own temperature, still keeps its own temperature. So it brings actually colder air to a warmer environment, right? So the theta p minus theta e is going to be the fluctuation of the temperature, and this is, we know from this figure, in this environment is going to be negative. So W prime theta prime here is going to be negative, smaller than 0. What does this mean? This means that turbulent eddies move colder air cooler air higher, right? So this is how it happens here in this situation. Okay, so this is the first scenario, and then the second scenario, we can have something like this again, but now the parcel air, let's say the air parcel, an air parcel moves downward. So let me show it with this. So this moves downward. So W prime is negative. So this is theta P and this is theta E. So once it comes down, then this parcel has the, let's say, is warmer, right? Is warmer than its surrounding. It has this temperature of theta P. So here, this theta prime is going to be theta P minus theta E, which is going to be positive here, okay? So theta prime is positive, and so W prime theta prime is going to be negative here again. And this means that the turbulent eddies move warmer air lower. Okay. So this is the nighttime case with surface cooling. And then we can have another case, which is daytime case with surface heating. And that means that partial T over partial Z is greater than 0. So surface cooling is that this partial theta over partial Z is smaller than 0, is negative. But here we have surface heating. So let's look at these cases now. So when we have surface heating, the surface especially during daytime, because sun kind of shines over the surface, and then over the surface kind of hits the surface, So the temperature near the surface is kind of higher than the temperature farther aloft. So what is going to happen here? We are going to have two cases similar to the other one. First, let's investigate when an air parcel goes up, and then the second time when it comes down. So when an air parcel goes up, here, W prime is positive, right? So it goes up. How about the temperature, the theta prime? You see it's theta P and theta E. So we have a warmer parcel in a colder environment. So theta prime is going to be theta P minus theta E. Which is positive. So W prime theta prime bar is going to be positive here. So turbulent eddies move warmer air higher. Now let's look at the other case where we have this downward movement. So here, W prime is negative. And this is theta E, theta P, and then theta E. But now, theta prime, which is theta P minus theta E, is also negative. So again, W prime theta prime in this environment bar is going to be positive. So this means that turbulent eddies move cooler air lower. Okay. So this W prime theta prime is very important surface heat flux, kinematic heat flux that is commonly being used, and it actually also defines what is known as stability in the atmosphere. So typically these daytime cases where we have a positive W prime theta prime or unstable atmospheric boundary layers or unstable atmosphere, and these cases where we have W prime theta prime negative, they are actually stable atmospheric boundary layers. So here, if you look at this budget, and then if you look at this budget also in the turbulent kinetic energy budget, which we didn't discuss about that, but this term actually goes also into the TKE budget. So what it does is when you have these negative heat fluxes, this actually kind of stabilizes the flow. And then when you have these positive heat fluxes, actually it destabilizes the mean flow, velocity actually, the mean velocity flow. And that's why we call this stabilizing or destabilizing heat fluxes or stable or unstable atmospheric boundary layers. Okay. So the last topic that I want to quickly cover here is that similar to the turbulent kinetic energy budget that we derived, we can also drive an equation for temperature variance. So similar to the turbulent, velocity variance that we derived, we can use the same similar technique and then derive the temperature variance equation. And I just want to write the equations here so you get familiar with that and see that you can use these techniques that we use for momentum equation for other scalars like temperature, even pollutants, or tracer gases or anything like that, okay? So let's go through this briefly. Temperature variance equation. So if you subtract the Reynolds averaged temperature equation from the conservation of heat we get the following. So if you subtract, this is the Reynolds average heat equation that we had, right? If you subtract this from this conservation of heat equation here, okay? In other words, let me write it down here. Let's say this is equation 2. And then this is equation 1. But this one, you need to write it in terms of the Reynolds decomposition. So I didn't do the Reynolds decomposition here. But essentially, here is going to be 1 minus 2 to get the following equation. You will get the following equation: partial theta prime over partial t plus u bar j partial theta prime over partial xj plus u prime j partial theta bar over partial xj plus u prime j partial theta prime over partial xj equals to nu theta partial square theta prime over partial xj square plus partial u prime j theta prime over partial xj minus 1 over rho bar cp partial q prime j over partial xj. Okay, so this is the equation that we are going to get simply by subtracting the Reynolds average temperature equation from the conservation of heat equation. So now, if you multiply this equation by 2 theta prime, again, a similar technique that we used before for getting the velocity variance, and then use the product rule of calculus and do the Reynolds average. So Reynolds average the remaining equation, will get the following, which is actually the temperature variance equation. So we are going to get, I don't repeat that again, I just write the final result here, which is going to be partial theta prime square bar over partial t plus u bar j partial theta prime square bar over partial xj equals to minus 2 u prime j theta prime bar partial theta bar over partial xj minus partial u prime j theta prime square over bar over partial xj minus 2 epsilon theta minus 2 over rho bar cp theta prime partial q prime j over partial xj bar. Okay, so this is the equation for the variance, temperature variance equation. And let's look at actually what each of these terms mean. So the first term is the local storage of temperature variance. Okay. The second term is the advection of temperature variance by the mean wind, right? What does this term represent? This term represents actually the production term. Is similar to the production term in TKE budget, right? But now we have it with the temperature. It's the turbulent potential energy. They sometimes call this TPE equation, like the TKE equation. Yeah, this is the turbulent potential energy equation, okay? So this is the production of the temperature variances. What is this term? This is actually a transport term. This shows the transport of this variance by the wind fluctuations. This term is actually the molecular diffusion or dissipation, molecular dissipation of this TPE budget. What does the last term represent? This is also a dissipation term, but radiation dissipation. So this is the dissipation of the temperature variance by the radiative forces. Okay. So this is actually, I wanted to show that you can also use the same concepts for scalars like temperature, and then get similar equations for the transport and the variance of these scalars. So let me wrap up what we learned today. We started with scalar dynamics in turbulent flows. We talked about what is the difference between an active scalar and a passive scalar. And then we wrote the conservation of heat based on the first law of thermodynamics, which is written here. We discussed the different terms in this equation. We did the Reynolds average heat equation, so we looked at that. Also, we did the Reynolds average, so we did Reynolds decomposition and looked at the Reynolds average that, and looked at different terms. So we talked about each of different terms. Then we talked about the kinematic heat flux that comes from here, W prime theta prime, this Reynolds decomposition, and then Reynolds averaging term that comes here. So we talked about what does it actually represent. For example, in the case of the atmosphere, when we have a nighttime case with surface cooling, and then we have a daytime case with surface heating. And then we talked about this temperature variance equation. So in the temperature variance equation, we just said that we can get it by subtracting the Reynolds average temperature equation from the conservation of heat, and then this will give us this equation, and then by multiplying this by 2 theta prime and use the product rule of calculus and Reynolds average the remaining equation, Reynolds averaging the remaining equation, we will get this equation, which is actually the temperature variance equation. And then we discuss different terms of that, like the production term, transport term, and then dissipation term. So dissipation of the temperature variance. Okay, thank you very much, everyone.